All right, welcome you guys to 1.2 part 1. So in this section, we're going to be talking about what a function is in detail and function notation. Okay. We're going to be moving away from, slowly but surely moving away from using y, and instead of using y(f) of x, and we'll talk about that. So let's talk about what a function is. So it says here, a function is a correspondence between a first set called the domain and a second set called the range, such that each member of the domain corresponds to exactly one member of the range. So we're going to look at a few different ways to look at this. We'll do some mapping diagrams, we'll do some ordered pairs, we'll do a graph, okay? So here's a mapping diagram. Okay, so when we're looking at a mapping diagram, we want to make sure every x value or every element of the domain goes with exactly one element of the range. So you can see here, -6 is only going to one value in the range, so that's good. +6 only has one arrow coming out of it, so that's good. Same thing for -3, 3, and 0. This looks good since every element of the domain maps to exactly one element of the range. So we're going to go ahead and say that this is a function. Oops. This is a function since every element of the domain maps to exactly one. I can type, I promise. Exactly one element of the range. Okay. Now, the fact that this 36 has two arrows going to it, it doesn't matter. We didn't say every element of the range can only go with one element of the domain. So we're really looking at this one way, okay? We want to make sure that the ones on the left only have one arrow coming out of them. It's okay that two arrows go to 36. It's okay that two arrows go to 9, at least if we're looking at functions. All right, let's take a look at this one. So this correspondence here was mapping diagram. It shows George Bush only picked one Supreme Court justice, right? Clarence Thomas. But Bill Clinton picked 2. George W. Bush picked 2, and Barack Obama picked 2. So on this one, we're going to have to say that this is not a function. Okay, so this is not a function. Oops. This is not a function since there are elements of the domain that have 2 arrows coming out of them. Okay. Let's see here. Bill Clinton, George W. Bush, and Barack Obama picked 2 Supreme Court justices. Okay. All right. And let's just highlight, what the problems are. Okay. So the problems are going to be this one, and that one. Okay. All right. Now we're looking at it through ordered pairs instead of through a mapping diagram. So I can see right here that 9 is going with -5. It's corresponding with -5. And 9 is also corresponding with +5. So we're going to say this isn't a function. This isn't a function since the x value, oops, sorry you guys, I'm in this text box and it doesn't have the normal functions. Okay. Oh, I pick italics over here. Got it. Okay. Since the x value of 9 maps to 2 different y values. Okay. All right, when we look over here, -5 is only going with 3, 0 is only going with 3, and 6 is only going with 3. So this one is good to go. This is a function since every element of the domain corresponds to exactly one element of the range. Okay. So hopefully for these two scenarios, given a mapping diagram or given a list of ordered pairs, you can tell whether or not it's a function. So if we have a graph, we use the vertical line test to be able to see if we are looking at a function or not. So let's just kind of talk about why we use the vertical line test. Okay. So let's say that I have the following graph. X equals the absolute value of Y, okay? And let's get some actual points here. I'm gonna take this a tiny bit more that way. There we go. So we'll say this is 2 and this is 3. Oh boy, I think I'm gonna have to rotate it more, you guys, to make it match the other one. All right. Close enough, I guess. Okay. So the reason why we draw a vertical line to check, right? So I'm going to draw a vertical line, and a vertical line is going to touch twice. Well, the reason why a vertical line works, because if you think about it, these ordered pairs, this one's 2, 3, and this one is 2, -3. So if you go back to that previous example, right, this example right here, okay, 9 showed up twice as an X value, right? 9 went with -5 and 9 went with 5. Well, we have that same situation here. 2's going with 3 and 2's going with -3. So drawing a vertical line will reveal an X value that's going with 2 different Y values. All right, so if we draw a vertical line anywhere, we're only going to touch one time, right? And so because of that, this one is a function. Okay. But over here, we can see a vertical line touches 3 times. So this is not a function. We can put down a vertical line touched more than once. Okay. All right. Go over here, same thing, not a function. For the same reasons, right? It ended up touching twice. It touched here and it touched there. So not a function. Same thing here, touched twice, right? So this one is also not a function. On this one here, no matter where we draw it, it looks like a vertical line is just going to touch one time, you know, no matter where we draw it. So this is a function. And this one's tricky. So let's go to the tricky spot. The tricky spot's really right here. Okay. So it is a function because technically that line only touched once. It touches here, but it does not touch here because there's no point there. There's an open circle, which means that there is no graph there. Okay, so we're good. We really only touched once. Okay, so it is a function. Since one of the circles is opened, is open. If it had been closed, right, we closed this up, then that would be a no because we would technically be touching twice. Okay, all right. Sorry, my writing's really bad. Hopefully you can read that. Okay, so now we're going to talk about the notation for functions and the importance of it. Okay, so we're going to be replacing y with f of x. These are the same thing. So like in the past, you might have had like y equals x squared. Well, in the future, you might see that we just write f of x equals x squared. Okay. And it's a better notation. You can see right here in the second paragraph, the beginning of it, why it's a better notation. Instead of writing when x equals -2, the value of y is 10, we can simply write f of -2 is 10. So like for an example, like let's say it's this one right here, okay? If I were to plug in a 1, right, in y equals 1 squared, we get 1. And then if I plug in a 2, we get 4. And so here it's y equals 1. It's y equals 4. So when I see this 1 and this 4, I've lost what the x value was that goes along with it. But over here, if I use this other notation and I say, okay, f of 1 equals 1 squared, f of 2 equals 2 squared, and you get your 1, and you get your 4, right? Okay. Over here, when I just write y equals 1 and y equals 4, I can't tell what the x value is. But over here, when I have like f of 1 is 1, f of 2 is 4, it's much clearer, like, oh, okay, I got 1 when I plugged in 1. Oh, I got 4 when I plugged in 2, okay? And you can see that often we call functions f, g, and h in this class, but it says here, as you progress, you'll see some other names for functions. And these letters actually tell us, like, this is my profit function. This is the velocity. This is the acceleration. So when we see something like v of 2, it says a lot. It says that's the velocity at time 2. So if I put like 10 feet per second after it, it's like, oh, okay, I know exactly what this 10 was. This 10 was the velocity at time 2. Versus if I just had y equals 10 feet, I wouldn't know what the x value was, but I also wouldn't know what type of a function it was. I wouldn't know, oh, that's the velocity. So this is just really much more concise. It says a lot more, and it says it efficiently, okay? So we're gonna try to like put in the f of x more often instead of the y. And in the class, basically anytime you see f of x, you kind of wanna think of it as a y, or you can replace it with the y. All right. So here we go. Here's a function where instead of writing y equals, right, we put f of x equals. A function f is given by f of x equals 2x squared minus x plus 3. Find each of the following. Okay, so this notation looks like multiplication. It really can be confusing because up until now, anytime we saw parentheses like this, that would mean f times 0. But this does not mean multiply. So I'm actually going to like write that in right here, that this does not mean multiply. In this case, parentheses do not mean multiply. Okay. So that gets a few people. Okay. So then what does it mean, right? Okay. So what this means is, remember, this is f of x. So what they're doing is they're giving you the x value. So you're going to substitute or plug in 0 for all x's. Okay. So the math for this, right? So what's f of 0? Well, we're going to go up here to the function, and anywhere where we see an x, we're going to put a 0. So when we're doing this, you have to follow PEMDAS, right? The parentheses, exponents, multiplication and division from left to right, addition and subtraction from left to right. So I'm going to do the exponents first. So 0 times 0 is 0. And then I'm going to go ahead and combine these two. Why not? So that's going to just get us 3. Positive 3. Because basically anytime you see a 0, you can just cross it off, right? Okay, so then 2 times 0 is 0. And 0 plus 3 is 3. So moral of the story, how can we get this fast? If you see something like this, you guys, I just cross off anything with the zeros in it and think, okay, it's just the positive 3. So here is our answer. F of 0 is 3. That's actually the ordered pair 0, 3. Because remember, f of x equals y. So they're giving you the x value and they're giving you the y value. All right, let's go ahead and try our B. So we're going to go ahead and substitute in or plug in -7 for all x's, right? Okay, so let's take a look at what that looks like. So f of -7 equals 2 times -7 squared minus -7 plus 3. All right, so remember, just like we said last time, according to the order of operations, you've got to do exponents before multiplication. I get a lot of students who multiply that, right? So we're going to do the -7 times the -7 first, okay? All right, so -7 times -7, well, negative times a negative equals a positive, and 7 times 7 is 49. And then right here, these two negatives, right? A negative times a negative equals a positive. So we're going to have a +7 on this line. All right, so 2 times 49 is 98. And I'm just going to go ahead and combine the 7 and the 3 because they're kind of nice. They make 10. And so it looks like we're going to get 108 for part B. Right now, we're going to be substituting in 5a for all x's. Feels really weird. Sometimes you'll actually plug in some sort of x for the x, and that feels really weird. Like in calculus, you might plug in an x plus h in there, okay, and that definitely feels strange. Okay, so we're going to put a 5a in for all x's. So again, we have to do 5a times 5a, right? You got to do the exponents first, you guys. Okay, so 5a times 5a. Well, 5 times 5 is 25, and a times a is a squared. So 2 times the 25, because now we can do that, right, is going to be 50. So we got 50a squared minus 5a plus 3. Now stop here. I always get some students that go too far with it. They're like, well, let me factor it and let me solve it, right? You can't solve it if it doesn't equal 0, okay? So I'm going to put a little note here. Be careful. Don't try to solve this. In general, you can't solve if it doesn't equal 0, okay? Okay. All right. And this one, we're going to substitute in an a minus 4 for all x's. Okay. So f of a minus 4 is going to be, make sure you use parentheses here. I didn't on the others because they were a single term. I have to on this one because I have 2 terms. And that's important because the negative is going to distribute to the second one, changing its sign. Okay. All right, now remember, exponents come first. So I'm going to have 2, but then I have a minus 4 times a minus 4. See, if you don't have those parentheses, you guys, you'd have the wrong sign on the 4. So important that we have those. So let's do some of the dirty work off to the side here. So what I mean by that is we got to FOIL out a minus 4, right? And there's formulas and stuff for this, but I try to use the least amount of formulas possible because, you know, it's hard to memorize a lot of stuff. And these middle two always combine. So negative 4a and negative 4a make negative 8a. So that's what we're going to bring back into our problem for the a minus 4 times a minus 4. And we might as well combine this 4 and 3 to get us 7, right? A little bit less to write. Okay, I'm going to distribute the 2. So everybody's going to be twice as big. We're just going to combine like terms here. Okay. So 2a squared. Well, you know what? Let me write this a little bit further over, you guys. That's my highest exponent. And then we're going to go ahead and combine the a's here, right? We've got a negative 16a minus 1a. That's going to get us negative 17a. And then we've got some constants here, like 32 plus 7, which is going to get us 39. And again, don't solve it. This is f of a minus 4, okay? Do not solve. This is actually a question on the final, I believe. Okay, graphing using tables. All right. So they've already picked the x values for you. So you're just going to substitute them in, okay? So if negative 3 is my x, negative 2 is my x, negative 1, 0, 1 squared. I'll just do parentheses on all of these, you guys, just to be consistent. 2 squared minus 5. And 3 squared minus 5. Okay. So negative 3 times negative 3, a negative times a negative is a positive. So it looks like we're going to get 4. Negative 2 times negative 2 is 4. So negative 1. Negative 1 times negative 1 is 1. So negative 4. 0 times 0 is 0. So negative 5. 1 times 1 is 1. 2 times 2 is 4. And 3 times 3 is 9. Now you'll notice we got some of the same values out, right? We got some repeats, and that's just because negative 3 squared and down here positive 3 squared, they're both going to get you 9s. So that's why we ended up getting the 4 twice, right? We got the 4 here and we got the 4 here. Same thing's true about all of these negatives. Negative 2 squared and positive 2 squared, they're both 4s. So we got the same answer there. So we're going to get some symmetry. You're going to see in this problem, we're going to have some symmetry in it. Okay, so we have to graph the ordered pairs, negative 3, 4, negative 2, negative 1, negative 1, negative 4, 0, negative 5, 1, negative 4, 2, negative 1, and 3, positive 4. So let's go graph these, okay? All right, negative 3, 4 would be, so negative 3, then up 4. Negative 2, negative 1. Negative 1, negative 4. 0, negative 5. 1, negative 4. There's that symmetry showing now. 2, negative 1. And 3, 4. So we have symmetry about the y-axis here. Later on, you'll learn that the reason why we have symmetry about the y-axis here is because it's an even function. I kind of missed a dot. We'll just make that dot a little bigger. There we go. Okay. All right. So now let's say you're graphing that you have to pick these x values, you guys. And I've told you before, if like you're graphing it and it's not enough, you can't tell what it is. You know, you're like, dang it, I don't know what that is. Does it go like this? Does it turn around? Then just plug more x values in until you can see what it's going to do. Okay. These first two, I kind of picked the x values for you. But on the last one, we're going to pick them. Okay. All right. So on this one, same thing. We're going to substitute in a negative 3. Negative 3 times negative 3 times negative 3 is negative 27. And we know that the minus a negative really means plus. So this is going to be negative 24. Now, is negative 24 on our graph paper? No. So we're not going to graph this. We're just going to say out of the range, right? Or too big. How about that? No. We'll say not on graph. Okay. All right, so we're going to substitute in, and this is more realistic, by the way, you guys. This is how you would probably do things. You'd be like, oh, dang, that one didn't work. Okay. Let me go smaller then. All right, so negative 2 times negative 2 times negative 2 is negative 8. Again, we know that minus a negative means plus. Negative 6, hey, is negative 2, negative 6 on the graph? Close enough, right? We'll say this is negative 6 right there, you guys. Okay. So we'll substitute in negative 1. So negative 1 times negative 1 times negative 1 stays negative. But we're going to get a plus 1 because of the minus and negative. So we're going to get negative 1, comma 0 as our ordered pair. All right, we're going to substitute in 0. So 0 cubed minus 0. Well, that's 0 minus 0. So the origin is in the graph. All right, we'll substitute in 1. 1 times 1 times 1 is 1. Take away 1 is 0. Wow, lots of zeros here, huh? 1, 0. And then 2 cubed minus 2. So 2 times 2 times 2 is 8. Take away 2 is 6. So 2 6s on the graph. Over 2, up 6. So again, we'll just pretend 6s right there, you guys. And then the last one to substitute in, 3 cubed minus 3. So 27 minus 3. Oh my goodness, this is going to be too big again. So we'll go ahead and say not on graph. Okay, so if we go into graph this, it should look something like that. Okay. And if you're using MyMathLab to do this, it pretty much graphs it for you as long as you have enough points, the amount of points it requests. Okay, you'll just click the graph button and it'll graph it. All right. Now, on this one, I actually asked you guys to pick the X values. I said, can we pick any values for the inputs? Okay, so let's investigate that. If we were to pick, like, let's say negative 5. We substitute in negative 5. We end up with a negative under the radical, which means we know that it's imaginary. And remember, this is the real number plane, right? There's only real numbers on here. We're not on the complex plane. So there's no imaginaries here, okay? So we can't go picking stuff like negative 5, negative 6, negative 7. The smallest value we can pick, okay, the smallest value we can pick, I claim, would be negative 4. Okay, so we'd have to pick negative 4 and up. Okay, so we don't want to go picking X values like negative 5, negative 6, etc., because those are going to give us imaginaries. So we can pick negative 4, right? Okay, now I'm going to pick negative 3. I'll pick negative 2 just to show you something, and then we'll talk. Okay, so let's start there. All right. So if we substitute these in one at a time, I'm just going to do them in blue so it clashes with this up here. Okay. So let's start by putting in negative 4. Negative 4 plus 4 gives us 0. And so what times itself gets you 0? 0 times 0 gets you 0. All right, and then we're going to substitute in 3, which is a good number because it gives us 1. And 1 times 1 is 1. Now, I don't think -2 is a good number. Let's see why it's not. -2 plus 4, that gives me something that is not perfectly square rootable. That gives me a decimal. We'll graph it and everything just so you can see that. But I'm thinking, man, I want to try to pick values that'll give me perfect squares like 1, 4, 9, 16, etc., right? 25. I'd love to get those values under the radical if at all possible. So I'm kind of thinking, okay, we've already gotten 1. So now I'm thinking, how can I get 4? So I'm thinking, how can I get 4? So what minus 4 will give me 4 is what my brain's thinking. And so maybe you can see that it would have to be 8 minus 4 would get you 4. So I'm going to pick 8. I'm going to try this again. I have to think, now I want to get, I've already gotten 1, I've already gotten 4, I want to get 9. So I have to think, what minus 4 would get us 9? Okay, what minus 4 would get us 9? So 13 minus 4, you guys, is 9. So why don't we pick those values then, 8 and 13? Because then when we substitute them in, we're going to get a nice number. Okay, so this one we already said was square root of 2, which is like about 1.4 if you put that into the calculator. So we're going to graph -2, 1.4-ish, okay? And then let's actually do the math here pretty for our notes and stuff, okay? So now we're going to substitute in 8. Oh, it's plus 4. Sorry, you guys, I wrote down -4. Let's do that again. Then these values are not what we want. I apologize. Okay, so let me try that again. I put -4, huh? So what plus 4 would get us 4? Well, it'd have to be 0, right? 0 plus 4 would get us 4. And then we want to get 9. So what plus 4 will get us a 9? 5 plus 4 will get us a 9. So we want to pick 5. Okay, so I'm going to do those up here. So it is 0 plus 4. So that gets us 4, which is 2. Because 2 times 2 is 4. And then 5 plus 4 gets us 9, which is 3. So we're making our lives easy. Now, could we pick any values we want as long as they're 4 and up? Sure. Then you got to go and graph those and stuff. So I was just trying to pick values that would give us nice numbers, okay? All right, let's graph these. So -4, 0. -4 on the x, 0 on the y. -3 in the x, 1 in the y. -2, 1.4. 0, 2. 5, 3. And so the square roots are half of the sideways parabola. We don't have the other half, you guys, okay? So anytime you see a square root, think that, okay, it's going to be half of a sideways parabola. Okay. All right. So it's actually kind of tough sometimes picking, you know, what you want to plug in for x. Okay, so we really have to think about what values will make it work. Use the graph below to find each of the following function values. Now, I want to remind you guys that we learned that f of x equals y. That's how we started off the section, f of x equals y, or talked about earlier in the section. So what they're giving you here is they're giving you the x value. X is 1. What you need to find is you need to find the y value, okay? So we're going to go to where x equals 1 in the picture. So x equals 1 right there, okay? And I got to get the y value. So let's see, 1, 2, 3 is going to be the y value, okay? So f of 1 is 3. Now remember we said f of 1 equals 3 is actually the ordered pair 1, 3. And that is what this ordered pair is. That's the ordered pair 1, 3. Let me actually do that on the other side. Wait, I should have done it in red. You can barely see it. There we go. Okay, so now for the second one, again, f of x equals y. they're giving us x is 2. So if we go to where x is 2 and we find the y value, 1, 2, 3, 4, 5, 6, 7, 8, 9. And of course, you could look over here on the x-axis to get on the y-axis to get these values. Okay, so that's the ordered pair 2, 9, right? Okay, so f of 2 equals 9 or equals 9. Okay, these are the answers. Just want to make sure that you understand that that corresponds to the ordered pair 2, 9. It's the same notation. So these are super easy. They're giving you the x's and you just need to report out what the y is. Okay, they're giving you the x, you find the y. Find the indicated function values if possible, and determine whether the given values are in the domain of the function. Okay. All right. So again, this is the x value, these are, right? So these need to get substituted in for x. Okay. All right, so let's start off with getting f of 2. So I'm going to substitute in 2 for the x, and that ends up getting me 1/5. So f of 2 equals 1/5. Okay. Let's go ahead and substitute in the -3. Now this is problematic because this gets us 0 in the bottom. You can't divide by 0. When you divide by 0, that's undefined. Okay. So what this means is that f of -3 does not exist. Since it is not in the domain. Okay. But just as long as you know that it does not exist, we're good here, but I just want to use that. Oh, it says, and determine whether the given values are in the domain. I didn't see that part, so good thing we wrote this. -3 is not in the domain since it makes the denominator 0, but 2 is in the domain since it does not make the denominator 0. Can't write domain today, huh? 2 is in the domain since it does not make the denominator 0. Okay. Let's talk a little bit more about that. Basically, if you want to find the domain, you take the denominator, just the denominator, you guys, you set it equal to 0, and you solve. So you're going to move the -3 or move the 3 over, making it negative. This is what x can't be. So basically, if you had a number line, right? Here's -3, you'd say open circle that. But any number this way is okay, and any number this way is okay. And that's why 2 is okay. Okay. So -3 is not okay. So from -infinity all the way up to -3, parentheses, because we don't want to include it, and then -3 to infinity. All of these numbers are the domain. These are the numbers you're allowed to plug in, and they'll get an actual value out. In other words, they won't make the denominator 0. Now, I'm only showing you this to preview something that we're going to do a little bit later, okay? But for now, as long as you know if it makes the denominator 0, that it does not exist and is not in the domain, we're good. All right, part B. Find the indicated function values if possible and determine whether they're in the domain or not. Okay, so we're going to substitute 9 in. So it looks like f of 9 equals 2. So that must mean that 9 was in the domain, right? 9 is in the domain. All right, let's go over here and try the other value of 4. F of 4, so we're going to substitute 4 in for x. And that gives us a negative, which means that this is imaginary. So f of 4 does not exist. Okay, And so the conclusion here is that 4 is not in the domain. Okay. Let's go look at some pictures really quickly of these last two examples so you can kind of see visually what's going on. Okay, so let me go ahead and I'll put in GeoGebra. All right. So the first one was 1 divided by x plus 3, right? And as you recall, in this last slide, no, I'm sorry, I really pushed back. We said 2 was okay. 2 got us 1/5. Well, if you go to where 2 is, it does look like we went up 1/5 or 0.20, okay? All right, but the next one was -3. And if you look at x equals -3, there is a big emptiness in the graph here, right? And so that's why that is not part of the domain and why we get does not exist, okay? Let's try the next one, which was the square root of, is it x minus 4, you guys? X minus 5. Okay, so here's what the graph looks like. The values that we were supposed to find were f of 9, right? So when x is 9. Well, when x is 9, we do have a value and it looks like it's 2, right? We went up 2. So that's what we had. We had f of 9 equals 2. Then the next one that we were supposed to get was f of 4, and we said, well, it does not exist. Well, if you go to where x equals 4, right here, there is no graph anywhere. So that makes sense to say it does not exist there, okay? All right. It's nice to have that visual that goes with what we were learning. All right, you guys, that is the end of part 1 for 1-2. Take care.